Imagine all of space and time squeezed into a point smaller than an atom. That's the universe just before the Big Bang. Then, about 13.8 billion years ago, this tiny point expanded in a massive explosion. This wasn't an explosion space, it was the explosion space itself. The universe was incredibly hot and dense at the start, but as it expanded, it started to cool down. This cooling allowed the universe to evolve. In the first few minutes after the Big Bang, the universe was like a giant cosmic soup, a chaotic mix of energy and particles. This primordial soup was incredibly hot and dense, a seething mass of potential waiting to take form. It was filled with tiny particles like protons, neutrons, and electrons, the fundamental building blocks of matter. These particles were in constant motion, colliding and interacting in a high-energy dance. As the universe cooled, these particles began to combine. The intense heat and energy started to dissipate, allowing protons and neutrons to come together to form the nuclei of the first atoms. They formed the first atoms, mostly hydrogen and helium, the simplest and most abundant elements in the universe. These atoms were the first stable structures to emerge from the chaos. These simple elements drifted through space, clumping together under the force of gravity. Over time, these clumps grew larger, pulling in more and more atoms. Over millions of years, these clumps grew denser and hotter. The gravitational pull caused them to collapse inward, increasing the pressure and temperature at their cores. Eventually, the pressure and heat at their centers became so intense that nuclear fusion began. This process ignited the first stars, marking the birth of light in the universe. These stars would go on to create heavier elements, seeding the cosmos with the ingredients for planets and life. Stars didn't form in isolation. Gravity pulled them together into vast collections called galaxies. Our own Milky Way galaxy is just one of billions in the observable universe. Galaxies come in a variety of shapes and sizes, from majestic spirals to massive ellipticals. Within galaxies, stars live out their lives, fusing hydrogen into heavier elements. When massive stars die in spectacular supernova explosions, they scatter these elements into space. These elements become the building blocks for new stars, planets, and even life. Dark mysteries, unseen forces shaping the cosmos. While we can see stars and galaxies, they make up only a small fraction of the universe. These luminous objects, as beautiful and awe-inspiring as they are, represent just the tip of the cosmic iceberg. The vast majority of the universe is made up of something we can't see: dark matter and dark energy. These unseen forces dominate the cosmos, shaping its structure and evolution in ways we are only beginning to understand. Dark matter acts like invisible glue, holding galaxies and galaxy clusters together. Without it, galaxies would not have enough mass to hold themselves together, and they would simply fly apart. Dark energy, on the other hand, is a mysterious force that is accelerating the expansion of the universe. This repulsive force is causing galaxies to move away from each other at an ever-increasing rate, stretching the fabric of space itself. Scientists are still working to understand the nature of these enigmatic components of the cosmos. Through advanced telescopes and sophisticated computer models, they are piecing together clues about the roles dark matter and dark energy play in the grand cosmic puzzle. The quest to uncover these secrets continues, driving us to explore deeper into the universe and pushing the boundaries of our knowledge. Echoes of creation, the cosmic microwave background. If the Big Bang really happened, we should be able to detect some faint afterglow of that ancient event. And indeed, we can. This afterglow is a crucial piece of evidence supporting the Big Bang theory. It is a remnant of the intense heat that filled the universe immediately after the Big Bang, now cooled and stretched to microwave wavelengths due to the expansion of the universe. It's called the cosmic microwave background radiation. This radiation is incredibly uniform, but it has tiny fluctuations that provide a wealth of information about the early universe. This faint afterglow is like a baby picture of the universe, showing us what it looked like just 380,000 years after the Big Bang. At that time, the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms, making the universe transparent to radiation for the first time. By studying the patterns in this radiation, scientists can learn about the early universe and its evolution. These patterns reveal information about the density, temperature, and motion of matter in the early universe. They also provide clues about the formation of galaxies and large-scale structures. The cosmic microwave background is a treasure trove of information, helping us understand the origins and development of the cosmos.